Hi, my name is Kan Wu. Today, I'm going to present authors, an approach to optimize classic caching to manage modern storage hierarchies. This is a joint work with my co-authors from UW-Madison, Well, and Microsoft. Since the design of the first computers more than 70 years ago, storage hierarchy has long been central to system designs. It is a very important concept. Consider a simplified two-layer hierarchy to realize an ideal, fast, and large device to the users. Systems typically combine a fast performance device along with a slower but much larger capacity device. To manage such hierarchy, caching is the most important and popular approach. Like shown in this figure, caching leaves all data in the capacity device while replicating popular data in the fast performance device. To achieve good performance, caching always strives to direct most accesses to the fast performance device, and the wisdom is usually summarized as maximizing the heat rate. By maximizing heat rate, caching is able to deliver performance device-like speed and very large capacity. In traditional hierarchies where the performance device is much faster than the capacity device, caching hence works really well. However, within the modern storage hierarchies, caching along with the wisdom of optimizing heat rate is no longer sufficient. And the insight is the assumption of performance device being much faster than the capacity device no longer holds in today's hierarchies. Recently, with the development of non-volatile memory techniques such as 3D quadrupole memory, we have seen many new high-performance devices filling the performance gap between memory and storage. Excellent examples including byte-addressable NVDIMMs such as Optane DC persistent memory, as well as low-latency SSDs such as Inter-Optane SSD. These devices have become new layers in the modern storage hierarchies. Within the modern hierarchy, we observe that the difference between today's labeling layers are much less clear compared to that in the traditional hierarchy. For instance, we look into popular pairs of devices, such as DRAM over NVDIMM, NVDIMM over low-latency SSD, and compare low-latency SSD and conventional NAND flash SSD. According to our quantification, we find out the minimum performance difference across device pairs today are usually less than 3 times, and sometimes the performance of labeling devices actually can overlap. Consider a case in the Optane and flash SSD two-layer hierarchy. When serving reads with high parallelism, these two devices actually provide very similar performance. In this case, caching who optimize heat rate will be single-minded to direct most accesses to the Optane SSD, and it will leave huge performance available in flash SSD unexploited. Based on our observations, we believe it is imperative to rethink how modern hierarchies should be managed. In this work, we present a new approach called non-hierarchical caching, and in short, NHC. NHC follows the insight that we should treat today's hierarchy in a less hierarchical manner, and the available performance in capacity device should now be exploited. In NHC, we proposed a key idea to augment caching with dynamic load admission and request offloading. Our intuition is we should avoid excess load to the cache device when the device is saturated. These excess load examples include, first, admitting data into the cache device to further improve heat rate. When the cache device is already saturated, improving heat rate no longer helps, while the migration traffic actually can hurt the overall performance. Hence, we should avoid such admission traffic when the device is saturated. Also, instead of letting too many cache heats overload the cache device, we should bypass some of them to the capacity device to utilize the performance available in the capacity device. To realize our ideas, we present the design of non-hierarchical caching. As shown in the figure, first, NHC enables offloading by making caching behaviors tunable. As shown here, unlike classic caching, which behaves statically according to its policies, now NHC makes the decision points become tunable or dynamic. First, NHC introduced a data admit flag into the cache controller. This flag decides at any moment whether NHC will admit the read-miss data into the cache device. This flag is tunable during the runtime. Secondly, NHC introduced a load switch in the cache controller, which works with a parameter called load admit ratio. The ratio ranges from 0% to 100%, and the switch decides at any moment how many read heats will be really directed to the cache device and how many will be offloaded to the capacity device. With the capability to do offloading with our design, the next question we need to answer is, how much load should we offload to the capacity device? According to our investigation, we observed that different hierarchies, along with different workloads, will all desire different split of load to devices to achieve good performance. To handle such complexities, we introduced a feedback-based cache scheduler into NHC. As shown in this figure, NHC scheduler can adjust the tuning knobs we introduced in the NHC cache controller. And the scheduler turns to optimize a targeted performance metric. The metric can describe performance as either user or device level, and the metric can describe different aspects of performance, such as throughput, latency, and tail latency. All a user needs to do is provide a function f that can measure or compute the target metric, and the scheduler will use function f to optimize the performance. To show how the scheduling works, we next present an example run of it. First, NHC will always begin with classic caching. By doing so, the cache device is warmed up, and NHC ends the state when a relatively stable hit rate is detected. Then NHC starts to adjust the load across devices. It first turns off the data admission for read misses, and then it tries to turn the load admit ratio. As shown in this figure, at any time point with the current load admit ratio as x, NHC will try to get the function f value with both x plus delta and x minus delta. Then, like gradient descent, NHC will move the ratio towards the direction that will improve the performance. With continued tuning like this, NHC will be able to readjust the load across cache and capacity devices. It hence now can utilize the performance available in capacity device. It will also be able to handle changes in workload during runtime. Finally, NHC will end the state 2 when the workload hit rate significantly changes, or when it finds out the 100% load admit rate is always the optimal solution. It will then get back to the classic caching. Before we jump into the evaluation part, we want to emphasize some key properties of non-hierarchical caching. First, we should note that NHC is compatible with all previous caching implementations or policies. Secondly, NHC requires no special knowledge of device or workloads. Like we have shown, all a user needs to do is provide a function f to be used by NHC scheduler. Finally, NHC can adapt its behavior in response to changes in the workload. We have implemented the NHC in system called authors. The implementations include authors CAS, a block layer kernel module, as well as authors KV, a user-level caching layer for WithKey. WithKey is an asymmetry-based key value store. In our implementations, we support throughput, average latency, and P99 latency as the target metrics. And we evaluated our systems in all the device pairs we discussed before. The next group of results demonstrates the ability of authors to utilize the capacity device performance. In the figure, we present authors' performance in many different hierarchies, as shown as different groups of bars. For each hierarchy, we looked into workloads with different intensity. We define load 1.0 as the minimum read load to saturate cache read bandwidth, and we scale that workload to generate other workloads. In the figure, we plot normalized throughput of both classic caching and orthus. According to the figure, first we can see classic caching performance is always bounded by the cache device bandwidth. In contrast, since orthus now enables offloading, it can utilize the available performance in the capacity device. As such performance is considerable in modern hierarchies, we observe a significant improvement of orthus over classic caching in today's hierarchies. Finally, there can be many more hierarchies than we can investigate. Our results with simulated hierarchies can help users to predict how much benefit you can get when applying orthus in your cases. We provided orthus results in simulated hierarchies with 5 times and 2 times performance difference. Due to time limit, we will only leave pointers to many other experiments in the paper here. To conclude, in this work, through quantitative comparisons across today's popular storage devices and performance characterization of caching in both classic and modern hierarchies, we show how evolving storage hierarchies have strong implications for caching design. We introduced the orthus which optimize classic caching by dynamic load of admission and request offloading. With the good properties orthus have, we believe it is flexible to be applied in many scenarios and providing benefits. Finally, thank you for listening, and all questions are welcome.